So we kind of zoomed over some of the stuff. Like we didn't really spend any time on threaded fittings. We're kind of on flanged, but I just want to go back onto threaded fittings just for a moment. Okay, so we know what malleable iron is, okay, as opposed to gray cast iron. And so a lot of the fittings that we use in power piping are malleable iron fittings, threaded fittings. And ASME has 8.5 million codes for all kinds of different things, from elevators to amusement rides to whatever, escalators to whatever. And so they've got a whole bunch of codes specifically for manufacturers. And this particular code is called the B16.3, which is for if you want to make your own malleable iron threaded fittings, this is your code, okay? So when it comes to these fittings, we find that there are two classes of fittings. There's a class 150 and there's a class 300. Now, if I'm holding a class 150 in this hand and a 300 in the other hand, how do I know the difference? Well, here's what they got in common. They have to have the manufacturer's name or some kind of a symbol that represents the manufacturer. And I'm just making this stuff up right now, but I don't know, maybe, you know, this company uses a diamond and that one uses a heart and the other one uses a club or something like that, you know, something that is a unique identifier for the manufacturer of the fitting. It's got to be on there. But if I have a class 300 fitting, it's going to have a little bit more. Not only is it going to have the name or trademark, but it will have the numerals 300. So notice the 150 doesn't have anything stamped on it other than the manufacturer's info, but the 300 will say on it that it's a class 300 fitting. Plus, it'll have the letters MI, malleable iron. Then it'll say the size. So if it's NPS 1 or NPS inch and a half or inch and a quarter, whatever, it'll say the size. Okay, so now I can tell the difference between the 300 and the 150 malleable iron fitting. Now then, why would I want to use one or the other? Well, it all depends upon the pressure and the temperature that I want to use that fitting at. So, you know, people will say things like, yeah, that class 300 fitting is good for 250 psi. And my response to that is, yeah, but at what temperature? Okay, so the service conditions, we know that as metal gets hotter, it becomes weaker. So here we've got a column of increasing temperature in degrees Celsius. And what you'll notice is, say at 66 Celsius, this particular stuff here is good for 2070 kPa. And that class 150 fitting at 175 degrees Celsius is only good for 1050 kPa. And there's a note there too. Oh, permissible for service up to 186 degrees Celsius, reflecting the temperature of saturated steam at 10.3 bar. So really, you can't use this over 1030 kPa. And as a matter of fact, you're really stretching things then. Now, as for class 300 fitting, let's say it's NPS quarter to 1. That's the range of sizes. Well, this one here is good for 13,790 kPa at 66 degrees. At 175 degrees is good for 7990 kPa. You get the idea. Now, what they have in common is every time there's an increase in temperature, we see a reduction in the allowable working pressure. Then the other thing is, as our fittings become larger in diameter, Okay, we know that the stress in the vessel, in the cylindrical component, varies with diameter of the vessel. And so the larger the diameter of the vessel, the thicker a boiler shell has to be. Well, how do we deal with this with fittings? We don't make them thicker. What we do is we reduce the allowable pressure rating as the diameter increases. So for 1 1/4 to 2 inch, it's only good for 1,000 or 10,340 kPa, and for 2.5 to 3 inch, that malleable iron fitting is only good for 6,900 kPa. So just so you're aware, is as fittings increase in diameter, they are they're rated for lower pressure, and as their temperature increases, their pressure rating also decreases. And finally, class 150 is a weaker class. Class 300 is a very strong class. And what you're going to find is in powerhouses where we work, we're going to see a lot of class 300 fittings. Okay. Good with that? Now we're in the power piping code, and the power piping code is going to give us actual threaded joint limitations and what we can actually do with those fittings. So we've got these threaded fittings, we know what the fitting is good for, and then the code of installation of the piping. Okay, this is a fitting manufacturer code, this is the actual piping installation code, and it's going to say, look, if you got an NPS 3 threaded joint, you can only use it for a maximum of 3 megapascals. Well, the fitting itself, an NPS 3, could be good for up to 2070 megapascals, or pardon me, kilopascals, or 2.07 megapascals at 288. So we know it's a pretty strong fitting. It's good for 2.07 megapascals, but B31 says, no, you can only use it for up to 3. Okay, so that's fair. And then again, we find that as the fitting size gets smaller, the maximum permitted pressure under B31.1 increases. And again, that's for threaded joints. Basically, 31.1 wants to make sure that the pipe is assembled securely so it doesn't blow apart on you and hurt somebody. Now, do you got to memorize this stuff? I think what you need to know is as the class of the fitting increases, so does its strength. I think what you need to know is that fittings get weaker as they get hotter. And I think you need to know that fittings get weaker as they increase in diameter. And I think you also need to know that as threaded joints, that there's a maximum limit to the size of the pipe if you're going to be doing a threaded connection under the B31.1 piping code. And then maybe the last thing to know is, yes, there are codes, there are places where you can look to find this information. So if you download this PowerPoint, you can kind of print off some of the pages if you like, and kind of keep that in your back pocket, something to refer to in the future. Or you can get the source codes, whatever you like. Which now takes us to where we left off, which was flanges. And these pressure ratings, that's really the wrong word. It should be service rating. And the service rating is, again, pressure and temperature. Because we know that the pressure varies with the temperature of the material. And again, we got class 150, 300, 600, 900, 1500, and class 2500. Now this one here, that's big quinage, that's muchos doleros, But this would be what you see in, say, like a large thermal generating station that's, supercritical boilers, right? And it's a massive, very robust, very strong flange. Whereas a class 150 flange is the kind of thing that you'd find on the fourth floor of the Synovus building on the pumping lab, where you've got Schedule 40 pipe and you've got class 150 flanges. And what can they be made of? A carbon steel, stainless steel, blah, blah, blah. And I'm not going to go any more into that, but what I want you to see here is right there on the edge of this one. I can't zoom in on it, but you're going to have to take my word for it that there's all kinds of things hammered into the side of that flange, all kinds of data. Okay, and we're going to talk a little bit what has to be on the flange, and if it's not on the flange, you throw it away as far as you can or put into a dumpster or whatever. So again, ASME has a code for people who make flanges, and this code is saying, what do you got to put on your flange? Flange identification marks, B16.5 code. Maybe you don't design a flange to B16.5. Maybe you just sort of make one in your backyard and say, that's a good flange. Well, if you want to actually sell that flange, and if you want to tell a customer that it meets the quality requirements of the ASME code B16.5, then you have to follow that code and you have to stamp this on the flange. It'll either say on the flange B16 or it'll say B16.5. And if it doesn't, throw it away. And just like for the threaded fittings, we've got to have some kind of a name or trademark of the company. Maybe it's Crane, maybe it's, who knows, their company. The material designation also has to be stamped on it. Is it something like A105, which is a pretty common carbon steel flange material? Notice I didn't say SA105. We know that this is an ASTM designation for the material. We know by the letter A that it means it's a ferrous material, and we know that 105 is some kind of a catalog number. So if you wanted to look up the material specifications, its chemical composition, nominal chemical composition, if you want to find out what its manufacturing dimensional tolerances are, if you want to find out what its tensile strength and yield strength and all that kind of stuff, well, we can look it up, and we can, you can even Google A105 or whatever this flange material has to be, but it has to be stamped on the flange. So that's the ASTM specification. Then, and oh, look at that. We got to have the pressure rating class has to be stamped on the flange. And some of you who were playing with me with the pumps yesterday, we actually looked at one of the flanges and we saw that stuff. And then, of course, we need to know the NPS designation. Is it NPS 2? Is it NPS 3, 4, whatever? What's the size of the flange? So let's now take a look at this beautiful, beautiful slide. And I think that this is table A361 from the B31.1 power piping code. But let's just take a look here. This is maximum allowable working pressure. Okay, here's the thing. We can pull up ASME1 or we can pull up 31.1 and we can calculate for pipe and drum and header and tube and all that kind of stuff. But how do you deal with a fitting? How do you deal with a flange? Well, they tell you, so this is what they call a standard class flange. I put standard class flange. And the standard classes of flanges are 150, these here, those are the standard flange classes. Oh, look, on this other table here, it says standard class. Then there are special classes, but we're not going to look at the special classes. We're just going to look at standard classes right now. And so, oh, look at that. You have a code that tells the mop. Isn't that cool? So for saturated steam, oh damn it, this is PSI. Okay, we'll just deal with PSI. We're going to pretend you guys can do the times 6.9 business, okay? I'm not gonna. But, okay, a class 150 flange in saturated steam service, you can only use it up to 205 PSI. Okay, so maybe in a place like the powerhouse next door, if the boilers have safety valves set to 150 or something, you might see a lot of class 150 flanges. Class 300 flange, 605 PSI. And on and on and on until you get to the class 2500 flange, which is 3200 PSI. Oh my God. That's got to be above supercritical. Okay, note 3. What does note 3 say? Rating exceeds critical pressure of water. Okay, so if we've got a large supercritical plant, we're going to see a lot of class 2500 fittings. And of course, these are flanges. Now remember when we talked about boiler and feed water line, and we said that blow off and feed water are in a special category. We call that shock service. There's probably a reason why I keep talking about this. It might be important. And if we're going to determine the MOP of piping in shock service, we said that the MOP, we calculate the MOP and then we add 225 PSI, again, pounds, or we go 1.25 times the calculated MOP. And then we select the lower of those. Why? Because of the beating that those pipes take. They must be built stronger than the actual boiler. So here we got another column. This is not just for regular saturated steam, but this is for boiler feed and blow off, which is shock service. So for shock service, that same flange that was good for 205 PSI, now it's only good for 170. And that same class 300 flange that was good for 605, 490. You get the idea. So what do you got to get from this slide? What you got to get from this is, again, for flanges, we're not talking about threaded fittings now, but for flanges, we got all these standard classes, and as the class number goes up, so does their strength. And you need to know that the steam service rating is different from the shock service rating, and that the shock service rating is less than the steam service rating. Okay, that's what you got to get of this slide. And then I can take a look at these various standard classes and I can see how they vary with temperature. So maybe I'm not using them for steam, maybe I'm using them for process line of some type. So again, as temperatures increase, the material becomes weaker. That's what you got to get out of this slide. And one more thing, you got to know that there are places where you can look for the information. And it might just be a Google search away. Any questions about these standard classes? By the way, the whole standard class thing is pretty brilliant, because what it does is it forces manufacturers to all make something to the same quality, the same dimensions. They're all going to behave the same way. It doesn't matter whether you buy it from China or Germany or USA or Canada, right? As long as according to those codes, you've got what's called a standard class, and you now then as a designer can select the fitting that's appropriate for the application based upon the pressure and temperature. So now let's look at individual types of flanges. Here's a raised face flange. And this flange, if you take a close look at it, it could either have a whole bunch of concentric circles, or it might have like a spiral all around it, and they're just like grooves. And so the reason we're going to have grooves is to kind of grab onto the gasket, because we don't want the gasket to get blown out due to the internal pressure. So here is the raised face, and I'm going to put a gasket there. Oh, there we go. There's a gasket. Oh man, that's a mighty thick gasket. And then the other flange will be on the other side of it. And that gasket then is going to be exposed to the process fluid here, and whatever that pressure is. And then on the outside, it's going to have atmospheric pressure. So this fluid inside, maybe it's corrosive. Maybe it has a very high temperature, and that can weaken the gasket material and maybe make it crack and fail prematurely. So we got to select a gasket that's suitable for the temperature and suitable for the compatibility with the fluid that's in the pipe. And then finally, the magnitude of pressure. So find that the higher the pressure, the thinner the gasket, because that pressure is going to be acting on the inside cross section of that gasket. So it's acting on that area. Pressure times area is force. That pressure is going to be pushing out against the gasket, and maybe the gasket has been weakened a little bit from high temperature or corrosive action or whatever, and then boom, we get a blowout, and we'll get a big mess in the powerhouse, and people get burned and blah blah blah. So we don't want that. We don't want blowouts. So that's why we got grooves. The grooves kind of grab onto the gasket. So if we've selected the proper gasket material, and it's the proper gasket thickness, and it's appropriate for the pressure and temperature of the service, then those grooves are going to hang onto that gasket and prevent a blowout. Now this particular gasket has this flange, I should say, has a raised face. And so this raised face then makes it easier to compress the gasket to its normal operating thickness. Okay, so if we had a gasket that didn't have that raised face, we would have this large area here that really would not provide adequate clamping force on the gasket. So by using a smaller width of gasket and a raised face, we get a more better clamping down. We can concentrate the force. Oh, here it is. It's right on the slide. I got to read the slides every once in a while. It says concentrates the force on the raised face to handle higher pressure. So that's a good thing, and these are very common. So because the process fluid can be on one side of the gasket and atmosphere on the other side, we say that the gaskets are unconfined. And some may be full face and some may be ring. The ring gasket only goes on the raised face, but the full face gasket goes all the way through. It's sort of a waste of material, and then you got to have a bunch of holes punched into it. Sort of a waste of material, but it is what it is. Now this one here is a straight face flange, and notice it does not have the raised face. Okay, this one here would take probably a full face gasket, and it just does not give us the clamping force that we want for high pressure service. So generally speaking, we don't use these. Again, the gaskets are unconfined. Now these are usually cast, and B31.1 places limitations on cast flanges. So we're just going to try and stay away from them. So this one here is called the ring joint flange, and better to look in the upper right hand corner at this gasket here. That's the gasket, and it's actually a compressible, deformable metallic ring. And notice that it fits into a groove, okay, and there is a corresponding groove to the other flange. So what happens is it gets squished into that groove, and it gets squished into the groove on the other side, and really makes a very, very tight seal. So we say that this gasket is fully confined. You know, the pressure here and the liquid cannot act on the gasket, nor can the atmosphere. So it's a fully confined gasket, and so we will not get a blowout. No blowouts. That's a good thing. But these here are designed for higher pressure, so you won't find them in a class 300. You won't find them in a class 150. It's just sort of a waste of money. But class 600 or higher, that's where we start to see these RTJs. And notice too that these are also suitable for higher temperatures. So usually some sort of an alloy that is not affected by high temperature. Now this one here is similar to the RTJ. It's just tongue and groove. So here we can see here's a groove. And I just realized that this is a blank flange, but well, you get the idea. If there's a hole in here, it would be a pipe flange. And then here at this end here is the so-called tongue. Okay, the tongue is the sticky outy part, and the groove is the sticky inny part. And then what we're going to do is we're going to put a gasket in there, and we end up with a fully confined gasket. And fully confined is a good thing. We're not going to get blowouts. We get good sealing. Now these are expensive flanges too, but not as expensive as the RTJ. Plus, we're not confined to using these special ring joints. These ones here may be gaskets or other type of specialized materials. So, in terms of how we mount the flanges, we have got weld neck flanges. Unfortunately, not showing it here. This is a socket welded flange. So you can see here's the socket, and the pipe gets inserted at a certain depth, and we leave a little gap there. And that little gap is to permit linear expansion of the pipe downstream of the weld joint. And so what we have here is a full penetration weld joint that goes all the way around. That's one way that we can install a flange, and we call this actually a slip-on flange. But generally speaking, this is for smaller sizes, so up to NPS 2. We normally don't socket weld elbows or flanges or anything like that above NPS 2. So where is that? Yeah, so that you were just looking at a welded slip-on flange. Of the socket variety, I mean, this one here isn't even a socket weld. This one here, they slip on the end of the pipe, and the flange goes there. And what they do here is they prepare the pipe, they bevel it first, and so they weld it there, and then they do an outside weld. So that's one type of welded slip-on flange, but the one we looked at on that slide was actually socket welded. As for screwed flange, this would be for low pressure service. You know, again, it's got the same limitations of having to thread pipe. And then maybe 31.1 might step in and say, no, 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 you can't thread that pipe. It's too large. Here I am rambling away, and we've gone over time, and it's time for a break. My apologies. Let's take 10. And when we come back, we are going to look at butt welded flanges, butt welded pipes as a method of assembling piping systems. So come back at 5 minutes after 4. Hey Google, set a timer for 10 minutes. All right, 10 minutes is up. So, yeah, threaded fittings, limited in size by B31.1, blah, blah, blah. Flange fittings, yeah, they're wonderful, especially when you got to dismantle, you know, take away pipes and put them back together, and service equipment. Very, very useful for that, and capable of handling high pressure as well. Of course, the ultimate is welding, and so we looked at socket welding there for up to 2-inch pipe. But now, what if we got pipe that's over NPS 2? Well, we're not going to socket weld it. We're going to be butt welding it. And so here you can see a couple of pipes, pipe number 1 and pipe number 2, and we're going to connect them together by welding, by butt welding. So what we do is we butt them together. And so in order to, first we're going to bevel the edges. So you can see the bevels there. And what we're going to do is have what's called an open root. An open root means, here, I don't have a backing ring. If I have a closed root, it's essentially a fillet weld, but this here is what we're going to call a groove weld. And the reason I'm showing you this is so you understand how difficult this is to do. Okay, so you have to be a pretty talented welder to butt weld 2 pipes together to an open root without burning through the material, without making globs of metal inside of the pipe that we call grapes. That's a slang term because they kind of look like, you know, grapes, I guess. We don't want that inside the pipe. We don't want to burn through the metal. And so what we have to do is get a really talented welder to butt weld this pipe. And so what this welder is going to do is get a pressure welding license. And so they're going to contact ABSA, or whoever the authority is with jurisdiction, and they're going to go to the ABSA Weld Test Center. And then this person is going to take this pipe and is going to put some tack welds in there. So tack weld the pieces of pipe together, and then get the inspector to take a look at it. And if there's any cracks in it, then it's no good because the crack becomes part of the weld. So that would be an immediate fail. So the tacks have to be excellent quality welds. And after it's tacked properly, then the welder puts in the root pass, which is that very first pass. Okay, and then calls the inspector over and says, hey, take a look at the root. And then the inspector takes a look at the root, and it's going to be looking for grapes and burn through. It's going to be looking for undercut. The inspector is going to be looking for cracks. All of these conditions that will fail the welder. And if that looks good, then what the welder will do is fill it and cap it so that we've got a complete weld joint. And that's not enough yet. Then what happens is the weld inspector is going to cut this up into coupons and is going to give it a tensile test, and it's going to give it a bending test on the root, and it's going to bend it on the face, and then maybe send it for radiographic examination as well. And once it passes all that stuff, they give this guy a pressure welder certificate. The guy welded a groove weld to an open root, so this guy or gal can weld anything. Pretty much, okay. When we get into welding, we'll go into more of the nuances about what exactly a welder can weld. But what if you're not a very good welder? Well, then what you can do is you can put what's called a backing ring. And you should know too that they're also called backup rings. You might come across that term as well. And so now what we have is material that's behind the weld joint, and it helps to prevent burn through. It helps to prevent grapes. It helps to make the weld. Makes it a little bit easier. It even has these little sticky outy things, and those little sticky outies there maintain the optimum gap between the two pipes that we're butting together. So when are they used? They're used when a weld engineer specifies their use, and that's about it. So they help with alignment. So if people are having trouble aligning pipes or the alignment is critical, and they prevent burn through. So really they make the fit up and the welding easier, and actually it becomes part of the weld. So this metal here actually becomes part of the weld, and then the weld groove is going to be along here, and it'll probably melt right into it. So this will actually become part of the weld material. So the backing ring will either stay in place, but in some situations it can be removed. But if it stays in place, it presents certain problems. First of all, there's a place where fluids can swirl around and wear away, so we can get erosion. And we saw earlier, caustic gouging going on beneath the backing ring. That was one of the slides that I showed back in corrosion. Also a little bit of a flow restriction, more turbulence and a diminishment of the cross-sectional area of the pipe. And it makes it more difficult to do non-destructive examination on the weld. When are they used? Like I said, when specified by the design engineer. Now, normally what we see is this here. This is a groove weld, and it's got a 35-degree bevel, which would give us, in this case, the whole angle there would be a 70-degree, and we call that the included angle. Now, what I'm used to is back in Manitoba, the Weld Test Center, the welders did a 75-degree included angle, which was a 37.5-degree bevel. But I mean, it really depends upon what is the code that somebody is welding to. And so this material is a particular thickness. And for some reason here, there was a backup ring. Oh, there's the word backup ring. There was a backing ring was specified for this particular weld. Now, typically we maintain a gap between the two pipes. And sometimes what we do can be very helpful is we can grind off the edges that are kind of flat, and we call that the land, L-A-N-D. Okay, and the land actually makes the material a little bit beefier at the edge of the gap so that you're less likely to have burn through. So it's very, very helpful to actually have a land. And so then, root pass, tack it, root pass, and then it's all subsequent passes to fill and cap the weld. So depending upon what kind of material it is, depending on how thickness it is, we might have to preheat or stress relieve. And the reason for this is, of course, body-centered tetragonal martensite formation. We don't want this martensite formation because it is brittle It's not ductile, and the weld joint could fail at this part that we call the heat affected zone. So to deal with the heat affected zone, we can preheat the weld joint so that it cools off slowly, because if you recall, when we looked at the iron carbon phase diagram, and we had the lower critical temperature, which was 723, and here we have the upper critical temperature, and here we had perlite and ferrite, and here we had perlite and cementite, and we said that it was the rate of cooling that created martensite, so that the phase change is not permitted to happen at its optimum rate, and instead of the austenite forming perlite, cementite, and ferrite, it forms a body-centered tetragonal martensite. So we have this heat affected zone, and it's all about the rate of cooling. So if we can preheat the pipe, then it cools slower, less martensite formation. And then the other term that they're using here is stress relief. And well, stress relief is just one method of post-weld heat treatment. And the whole idea, again, is to take that martensite after it forms, make the metal austenite again, and then let it cool slowly so it turns back into perlite and ferrite and cementite like we want it to be. So that's the welding. It gives you a little glimpse into what's coming up next when we get into welding. Gaskets. Wide gaskets. We want a positive seal under pressure. Compensate for minor surface flaws and minor misalignment. So some people think, oh, I can misalign my flanges like crazy. The gaskets will take it out. No, they don't. I can have flaws on my flange faces. The gasket will take up. No, it won't. It's minor, yes, and there's always going to be minor misalignment. You know, maybe a thousandth of an inch or something like that. That the gasket can deal with, but not gross misalignment. So we know about unconfined, we know about confined. Now there is also a semi-confined gasket where we are just going to confine the gasket on one edge. So in other words, it'll be protected from the process fluid, or it will be shielded from the atmosphere, one or the other. So let's look at that semi-confined. This is a male-female type. So here is the male flange face, and there's a corresponding female flange face, and the gasket's going to sit in there. Notice that it's not confined on that side, on the pressure side, but it is confined on the atmosphere side. And then, you know, there's another one here, groove to flat. The whole point of the matter is that the confined and the semi-confined are more suitable for higher pressure service because they're less likely to blow out. And there's a bit of a measure of protection too from process chemicals. Not entirely, but somewhat. We looked at the RTGs. Why are we back there? I don't know. So types of gaskets. Metallic gaskets are used for basically high pressure service, and they tend to be very resistant to process fluids. Process fluids, and also for high temperature. So high pressure and high temperature service. You know, it just can't keep up with my writing, so it just ends up being a real mess. Uh, Corrugated gaskets are pretty common too. Spiral wound gaskets, we see these a lot in natural gas service for high pressure natural gas. And we also see these for boiler manholes. Then we also have the non-metallic. And these include things like cork. We see these in automotive service for like valve cover gaskets or whatever, or oil pan gaskets. Rubber, Teflon, we see this actually in boiler handholds. A lot of manufacturers now provide Teflon handhold gaskets. Graphite is a really super gasket material. It can be a reinforced and unreinforced gasket. And then there is this one here, which is very, very important, asbestos. Did anybody hear that the city of Asbestos in Quebec changed their name? It's true. Because they didn't want to be associated with asbestos anymore. Anyway, this particular product is it's a wonderful gasket material. It's a wonderful all kinds of material. So here's the point that I want to make is if you are removing a gasket from any surface, whether you're scraping it or using a wire brush, find out what the material is. If it is asbestos, it must be removed according to a very specialized procedure. And you are likely not qualified to be doing that. So before you remove a gasket, find out what the material is. And if you're not sure, treat it as though it is asbestos. Don't ask me how I know this. But as you can see, we've got a great variety of materials that are suitable for different temperatures, for different pressures, fluid compatibilities, and on and on and on, right? So these are some of the things that we have to consider when we select a gasket. And so, I don't know, these are just some pictures from your textbook. I don't want to talk about them. Here's the spiral wound gasket. Unfortunately, they're only showing one half of it. What it should look like is flat part, spirally metal, and another flat part. And then there's the opening in the gasket. And then there's the other flat part, more spirally things. And then another flat part. And boy, I can tell you a story about this. I used to work for a company called Dow Corning, and I was in charge of commissioning part of the plant, which was called the off-gas handling system. And so we had these 3 big bag houses, and we had these Nomex bags inside of the bag house that were fire retardant. And this off-gas was at an extremely high temperature. And so after our first run, I went to inspect these bags to see if they survived the high temperature. And before I did that, I had to order some gaskets. So I ordered these spiral wound gaskets that were a quarter of an inch in width and about 3 diameter. And so they're very flimsy things, and they were shipped on pieces of plywood. They were stapled to pieces of plywood, okay, so that they wouldn't bend and flex and fall apart. Well, we were putting it back together, and I was working with this other guy. He was a third-class power engineer, and so we're up there on the baghouse area, and we've got these manhole openings are open, and we're time to put it together. And we looked at each other like, oh, we need some silicone. We need some high temperature RTV silicone to hold the gaskets in place while we close the door. And so I said, you wait here, don't touch anything, and I'll be back with the RTV silicone. I came back about 5 minutes later, two of these three gaskets, and they were about $80 a piece. He had dropped them on edge after taking them off the board, and they sprung out like the world's largest slinkies. Anyway, that's my spiral on gasket story for you. This one here is about effects of temperature on piping. And I think we know this. So let's open this up to the floor. What I want you guys to do is start shouting out what are the effects of temperature on piping. Let's see how many we can list. Starting now.
Expansion.
Yes.
Weakening.
Yes.
Corrosion.
Corrosion. Ah, yeah, that's a real interesting one because we know the corrosion increases at high temperature. So yeah, I'm going to put that one down there for sure, right? I mean, temperature, yeah, that surprised me. I don't have that on my list, but thanks for that. What else?
Contraction.
Contraction, yes. So often we think about high temperature, but let's put it this way. Where does it say high temperature? The objective says explain the effects of temperature on piping. It doesn't say high temperature. Okay, what else? What if the pipe was expanding and it had nowhere to go due to high temperature?
Bend.
Bend? Okay, give me a fancy engineering term.
Stress.
So stress due to restricted thermal expansion or contraction. Let's look at this weakening thing again. Yes, we know high temperature weakens steel. What else does high temperature do to steel?
Creep.
Right. Creep. Do you remember what creep is? It's a long-term plastic deformation of a material that's within its elastic limit, but exposed to high temperature for a prolonged period of time. And so some pipe is creep resistant, right? That's one of the effects of high temperature on piping. And in a sense, it's weakening. Weakens the pipe due to micro cracks forming. Okay, let's just see how well we've done. Thermal expansion, yes. Creep, yes. Thermally induced stress. Restrict thermal expansion. Oh, look at this. Low temperature. Yeah. So that's an effect on piping. Brittleness at low temperature. And so if we have a pipe that's being used in cryogenic service or refrigeration service, we might want to have steel that's alloyed with nickel to improve its nil ductility transformation temperature. Right, so we want to make it ductile at low temperature by adding nickel as one of the main alloying agents that increases toughness and ductility at low temperature and keeps it from getting brittle. What about this one here? Did we talk about graphitization? Okay, I think that in your textbook it says that graphitization occurs over 400 degrees Celsius. And I think ASME 2D says 427 degrees Celsius is when graphitization occurs, and that's when the carbide phase basically decomposes into iron and graphite. And graphite, as you recall from great cast iron, is weak in tension. So ultimately, graphitization, if we've got a particular type of pipe that's exposed to temperatures greater than 427 Celsius over a long period of time, plain carbon steel will, the carbide turns into graphite and iron, and then it becomes weak and it blows up. So it's one of the things we've got to watch out for, graphitization. And what about this one here, thermal shock? Do you guys know what that was? Let me give you an example of thermal shock, okay? This is a cold, high-pressure steam line. And it's really, really thick, high-pressure steam line. It's exaggerated. Actually, let's say it's a steam chest from a turbine, okay? Oh, no, this is piping. Okay, so it's got to be pipe. And when it's really, really cold, what I can do, I can take superheated steam at 600 degrees Celsius. And I'm just going to blast it through there without warming up the line. What's going to happen is I'm going to get great thermal expansion, but it's going to be restricted thermal expansion right on the inside surface of that pipe. It's going to exceed the elastic limit of the material, and then the next time, like when I turn off the steam and let the pipe cool down, when it cools down, I'm going to see cracks. Or here is another pipe. This is a superheater pipe, okay? And it's hot, it's at 600 degrees Celsius, and then I'm going to turn on the soot blowers, and unfortunately I got a slug of water in my soot blower, so here's a wave of cold water, and what I get then is this sudden thermal contraction. Boy. Shrinking of the metal right at the outside surface. Great stress. So both of these are examples of thermal shock. And so thermal shock is a temperature change a sudden temperature change accompanied by thermal expansion or contraction that causes failure of pipes. I had a better definition in my head before, but that's as good as I can do today. So as for thermal expansion, contraction, what do? We need these things. And you studied them last year, and I'm not going to go over them, other than to say this one here on the left is pretty neat because, we don't really have a lot of maintenance to do with something like that. It's basically just an accordion, and then this one here requires more maintenance. It's a pipe inside of a pipe, slides back and forth. We need to lubricate it. We need to have a packing gland. We got a drip connection here for a steam trap, that type of thing. So there's more maintenance with a slip type than there is with an expansion joint or with a corrugated type. And the other thing is that the corrugated type accepts a little bit more misalignment than the slip type does. So don't want to look at that one. Don't want to look at that one. You guys can study that. This one here is a really good one here because it's a tied universal expansion joint, and I think that your textbook has a different name for it, and it escapes me what the text calls it, but a tied universal expansion joint is a bellows type of joint that has rods and things that tie the flange surfaces together, and they're specially designed to accept axial and angular, I'm going to add that, and angular misalignment. So axial misalignment is if I got a pipe like this, another pipe like that, I take a look at their central axes and they're misaligned. And angular misalignment is like this. Obviously, we got this angle there is the misalignment between those pipes in an angular way. So what we're going to do is tie the flanges together, and we are going to put, in this case here, they're not all like this, but they're called gimbal joints. And the neat thing about this is we can use these without anchors, which really brings us to the little videos that I wanted to watch. Are we there yet? Not there yet. So, yeah, not going to look at that. I can't remember what I was going to say about it. Let's skip that one too. You can read over the expansion joints on your own, but what I wanted to do is look at anchors and guides. So let's take a look on the right-hand side. We've got a pipe that expands and contracts here, and we've got a pipe that expands and contracts here, and again. And so what we have here in the middle is an anchor. And now the guide is there to ensure that the movement back and forth is only axial, and it's not offset, it's not angular. Okay, the guide is there to ensure that the pipe goes directly in a straight line back and forth, because otherwise we could get a pipe that's going to do something like this. There's the expansion joint in the middle. It can actually buckle. The spring type of support, and then this one here is called a constant weight, a constant force support. And so you can read about this in your textbook. Basically, I've got a couple of springs of different spring ranges, and it's got some cam mechanism so that it's always providing the same support to the pipe, which is important if you get like hammer or shock or thermal expansion and contraction on the pipe. This one here basically compensates for all of that. Now here's an example of a pipe support, spring-loaded. Obviously, you know, the pipe rests on it. And here's another type of support that's very, very common in the industry where you see a riser. Oops, I don't want to do that. Where you see a riser. And so what they'll do is they'll weld the support directly on the elbow. And then what they have to do is make a little hole in here. And the hole is there just in case the pipe cracks, starts to leak at the corner. You'll notice fluid coming out, and that's called a telltale. As you can see, my pen doesn't want to work. Telltale. So a telltale hole. Now there's some information about piping supports, and this is B31.1. And so the question is, how closely do you support it?